In this video, I'm going to continue talking about nuclear magnetic resonance. And so in the previous video, we established that a nucleus with an odd atomic number, which allows there to be a net spin in the nucleus, or an odd mass number, so if we have an odd number of neutrons, we can get that net spin, has a nuclear spin that can be observed by the NMR spectrometer. So we are often talking about proton or carbon-13 NMR. I am mostly talking about proton NMR in these videos. I will make a video talking about carbon-13 NMR as well, but for now we are talking about mostly just proton NMR. So a proton has just a single proton, obviously, which has spin, and this can be modeled as behaving like a spinning and therefore moving positive electric charge. So the moving electric charges generate magnetic fields, which we symbolize with the B letter here with a little arrow over it because it's a vector. So protons are, however, surrounded by negatively charged electrons that partially shield them from the external magnetic field. So the electrons circulate and generate a small induced magnetic field that opposes the external magnetic field. So the vector for this induced magnetic field will be pointing in the opposite direction of the magnetic field, the external magnetic field that we are imposing onto the sample. As a result, the magnetic field at the nucleus of these protons is weaker than the external magnetic field. So what I'm saying essentially, and this is what I talked about in the previous video, if we have our proton here, it's positively charged, we are putting some magnetic field in, so we can call this our B sub naught right here. And so if this was just a naked proton, it would feel the full B sub naught on it. But we also have an electron that is spinning around it, and that is a negatively charged particle, and that will actually produce a field that is in this direction. So we can call that the B induced. So we can call that B induced. And so the magnetic field felt at the nucleus would be the B sub naught minus the B induced. So it actually feels a weaker magnetic field than what is actually in the external magnetic field. And so, like I said, the applied field must be increased for resonance to occur at a given frequency. So if we want a given frequency of our magnetic field to be felt inside, we would have to increase our external magnetic field in order to get to that level of magnetic field at the nucleus, because we have to overcome that B induced on there. So, like I said, the B effective, which is what is felt at the nucleus, is our external magnetic field minus the magnetic field induced on the electron, so the shielding of it. So we can think of the magnetic field from the electron as shielding the nucleus from the external magnetic field. And so it will feel a B effective that is less than the external magnetic field. And so because different atoms have different electronegativities and will pull or lose electrons away from themselves at different magnitudes, we can therefore think of these protons being in different chemical environments. And so one way we can do this is with inductive effects. So inductive effects means that the higher the electronegativity of one of the atoms near the hydrogen, the lower the electron density around that hydrogen. And so we can think about it this way. So if we just have this methyl group here with this hydrogen, and we can say this is bound to some hydrocarbon chain here, the carbon has an electronegativity of 2.5, the hydrogen 2.1, so there is very little difference there. But then if we bond this hydrogen to an oxygen instead, which has an electronegativity of 3.5, a lot of that electron density will be pulled away from the hydrogen. And so that is de-shielding the hydrogen because there is less electron density there. And so it's not shielding the hydrogen as much from that external magnetic field. And we can have this right here, so this is essentially the same as above, but now we're comparing it to this, where we have this oxygen that is one group away from the hydrogen. And so that is still going to pull some of that electron density away, but not as much as we see up here on this alcohol group. And so we can see that we get these different chemical or electronic environments based on what type of other atom is bound close by. And so we can look at it here. So if we have a methanol, then this alcohol hydrogen will be less shielded and it will absorb at a lower field, where these ones bound to the methyl group are more shielded and so therefore absorb at a higher field. So the hydroxyl proton is de-shielded somewhat in the presence of the electronegative atom, which is pulling some of that electron density away from it. So the diverse structures of organic molecules contain atoms with different shielding at different positions. So based on the position in the molecule, it will be in a particular chemical or electronic environment, and so it will therefore have a different amount of shielding. And what this means is that measuring the different shield strengths required for resonance of the various hydrogen protons give two types of information. One is the number of different signals or peaks, indicates how many different types of protons within a particular electronic environment are present. And so if you have, say, 3 peaks, then that means you have 3 types of chemical environments where your protons will show up. And number 2, the amount of shielding shown, and this is going to depend on where the peaks actually show up in your spectrum. So the amount of shielding shown at these absorptions indicates the electronic structure of the molecule close to each type of proton. And so what I mean by that is, like I said, say we have something that looks like this. So this is our spectrum here. So say we have something that looks like this, then another one over here that looks like that, and another one over here that looks like that. And so what we see is that we have 3 different types of proton environments. So there's peak 1 here, there's peak 2 here, and peak 3 here. And we see that this one is further this way, and so that means that this one is more de-shielded. So this is de-shielded, where this one is the most shielded right here. So that has the most electron density at it, which means that this one here must be in an environment where there are more electronegative atoms very nearby, where this one right here has fewer electronegative atoms nearby. And what you also notice is that I drew these peaks at different heights here. And so there are 2 other aspects of the NMR spectrum, and these are the intensities and splitting. So I didn't show splitting on here, and I will be talking about that in a lot more detail in the next video, but this is something that we will see when we are looking at these spectra. So the intensities of the signals, or the area under the curve on these signals, imply how many protons of each type are present. And the splitting, like I said, I will talk about that in a lot more detail in the next video, of these signals gives information about other nearby protons. And so the splitting will have to do with other nearby protons. And so if we see something like this, so again, we have our methanol, we see our de-shielded proton right here shows up down here, where these 3 right here show up over further to the right on our spectrum because they are more shielded there. So they are called higher field or up field, and we see that there are more protons there. There are 3 of them as opposed to the 1 right here, and so we will have more area under this curve right here than we will on this one. And so that tells us that there are 3 of these protons in this chemical environment right here, while only 1 is in this chemical environment. So that's why this peak has, well, we often talk about them as being higher, but what we're really talking about is the area under the peak. And so it is possible, as we'll see, especially when we get to splitting, that you can get peaks that look short but still have a lot of area under the peak. So the horizontal axis here is called the chemical shift, because we are looking at the shift based on the chemical environment of that proton, and this is based on the frequency, so the hertz, related to the magnetic field strength by this right here, where we have the magnetic field strength right there. So the chemical shift, it's the difference in parts per million, and as we'll see down here is parts per million because we are comparing hertz to megahertz, where a megahertz is a million hertz. So we're looking at parts per million between the resonance frequency of the proton being observed and that of a reference. The reference is often this tetramethylsilane right here. And the reason for that is because the silicon is lower in electronegativity than the carbons, and so it's actually going to be pulling electrons out towards these carbons here, and so that will actually shield those protons more than pretty much anything that you would see in the vast majority of organic chemicals. So the TMS, the tetramethylsilane, like I said, works well because it's less electronegative, so that the carbon and methyl groups are electron rich. And so we call that our 0, and that will actually be the furthest on the right on our spectra. So that would be probably somewhere over right there. And so the chemical shift, as I said, is the parts per million. So it's just the ratio of the shift downfield from TMS, so the tetramethylsilane. So we're looking at how much it has shifted away from that, divided by the total spectrometer frequency here. And so this is often done in this delta notation, where the TMS is defined as the 0 parts per million. And so we can see if we have a 60 megahertz instrument or a 300 megahertz instrument, the hertz on here will be different, but we can call the delta here the same on both of these instruments. So that gives us a nice standardized way of talking about these shifts here. So again, we're looking at our methanol right here, and we see that we have this peak for the 3 hydrogens in the methyl group shifted over here at maybe around 3.4, where this one right here is shifted down to maybe 4.8, 4.9, somewhere in that ballpark. And so we see that the one bound to the more electronegative atom is shifted to the left, where we have our TMS right here at 0. And so that delta is telling us the change in relation to the TMS standard. And so, as I said earlier, different elements bound to it are going to give us different amounts of shift here. So if we're looking at compounds bound to a methyl group, so fluorine or OH or chlorine or bromine and so on bound to our methyl group here, we can see how much of a chemical shift that will give us compared to our tetramethylsilane right here. So just the CH4, it's only about 0.23, but then we add this iodine, that shifts it to the left by 2.16, the bromine 2.68, chlorine 3.05, OH 3.40, and the fluorine 4.26. And so we can see here, if we compare this, so we just have a butane on the left right here, then we have a 1-bromobutane on the right here. And so we can see the shift for these protons. So on the two sides right here, it will be 0.9. The ones in the middle will be 1.3. But then if we compare that with the bromine, we get 0.9 over here, then 1.3, so those are not all that affected by the bromine. But then when we get here, this is shifted a little bit more, so by 0.4, and then when we get to the carbon right here where the bromine is bound, these two hydrogens will be shifted 3.4, which is 2.5 more than just the butane. And we can look at the additivity of these if we add more and more of one of these atoms to our molecule. So we have methane that will be at a delta of about 0.2, so very close to our TMS standard. We add a chlorine, and this will move it to about 3.0, so that's an increase of 2.8 parts per million. We then add another chlorine that shifts it to about 5.3. That's another 2.3 parts per million. A third chlorine will now shift it by 1.9 parts per million up to 7.2. So this is a figure from the book that I'm using for this, and it says each chlorine atom added changes the chemical shift of the remaining methyl protons by 2 to 3 parts per million. So these changes are nearly additive. And so we would see a different shift on this if we were adding, say, bromines or iodines or fluorines or things like that. So the electronegativity of the atom is the important thing here. Trying to interpret these spectra, you will often run across tables that look like these. So this one comes from the book I'm using, so it's showing a methyl group. The protons on that will have a shift of about 0.9. A methylene group, so one that's not terminal, will be about 1.3. The alkane, so if we just have this where the carbon is tertiary, now it's about 1.4. The methyl group bound to a ketone, so now we are next to that oxygen, which is going to shift it to about 2.1. This acetylenic one right here will be about 2.5. Then if we have halogens, it'll be between 3 and 4. The vinyl, 5 to 6, and so on and so forth through here. So you'll see these different tables, and I have another one over here, and so we can see that they don't always have numbers that exactly agree. So this one, the terminal one right here, instead of just 0.9, they say it's between 0.9 and 1.2. This one, this methylene group, is between 1.2 and 1.5. This one is 1.4 to 1.9. So we see we get some different numbers. They're all in kind of the same ballpark, but you do see that they give different numbers on a lot of these tables. You will often see tables that look like this as well. So this will actually show these ranges on here. So this is saying that this phenol right here and this aniline right here can show up between about 7 and about 3 down here. Then this right here, so this is X, is usually denoting a halogen here. And so we see this shows up between maybe 2.7 and maybe 4.9 on here. And so, like I said, you will get different numbers for a lot of these, but they are usually within the same ballpark. And so if we go down here, we can see that some of these groups will actually have some interesting effects here. So for instance, if we have a aromatic ring like this, what happens is the electrons in that pi system can actually go around and around on here. So we can get a current going on inside of here. And this will induce a magnetic field which goes out, we see, to right around where the hydrogens are. And so that has an induced field that will sort of add to our external field. So we now have this external field plus this induced field right here, which essentially makes the magnetic field felt by the proton stronger, which has the effect of making it look like de-shielding, because we are now getting this additive effect onto our external magnetic field. And so this is called diamagnetic anisotropy, which gives the benzene protons a greater shift than would otherwise be predicted. So we can look at this right here, which is a toluene, and we see we have, this is all hydrocarbons, so we don't have any oxygens or nitrogens on here to de-shield things, but this methyl group right here shows up way over to the right over here, where the hydrogens from the ring, which are gaining that effect, are showing up way over to the left here. So we would predict probably if this was just a cyclohexane that those would show up a lot closer to this over here. And so because of this induced magnetic field, this is actually showing up way over, usually between about 8 and 7 over here. And so we also see that we get de-shielding on vinyl protons. So again, we have these pi bonds on here, and this will have an induced magnetic field. The protons over here will feel more of that magnetic field, and so those will actually show up further to the left. And so we can see this right here where we have this vinyl group on here. So we see that this has the B, A, and C protons on here, and those are showing up over here. So we have the A and B right here, and we have our C proton over here. So those are showing up quite a ways over to the left compared to just the alkyl protons over here. And we see that these are showing up at around 5 and 6, which is what this figure tells us. But now, if we look at an acetyletic protons, so on a triple bond here, what we actually see is that this will orient sort of up and down in the magnetic field. And we now have the protons, instead of sticking out over here where the magnetic field is adding to it, it's now sticking up where it's getting into the part of the magnetic field that's going back down that way. And so this will actually have the effect of shielding the proton. And so we are adding to the induced magnetic field on the electrons. And so this will actually show up more shielded than would be expected. So we can look at this one right here for 1-hexene, and we get this delta 2 right here. And so that's actually showing up further to the right than this, which is one of these other protons right here. And so those ones are just alkane protons, so we would expect those to show up very far to the right. And so if this is showing up even further to the right than one of those, then that must mean that it's being further shielded by this induced magnetic field right here. So this is just kind of a summary of what we were talking about here. When we have a double bond like this or a aromatic ring like this, we get this B induced adding to the external magnetic field near the hydrogen, where when it's in alkyne, so an acetylenic hydrogen, we are now removing some of the magnetic field, the external magnetic field strength at the proton. We see a similar effect to this over here when we are looking at an aldehyde. So this carbon and this oxygen are double bound together, and we get this induced magnetic field that is going to help de-shield our proton right here. And so if we look at this, we see that this proton is actually showing up way over here, and in fact it's showing up at 10. And that's because we not only have this induced field reinforcing the external field, but we are also close to an oxygen, which will further pull some of that electron density away, even further de-shielding it. And so we get a lot of de-shielding on this aldehyde, so that shows up way over to the left at about 10. For carboxylic acids, we have a proton here bound to an oxygen, which is already going to have that electronegativity effect. But then we also have the resonance effect, so that can go there, that can go there, and so that will pull even more of that electron density away from the hydrogen. And so with carboxylic acids, this will be shifted even further to the left, and we see that this, in fact, is between 11 and 12. And so carboxylic acid protons usually show up about the farthest to the left that you will usually see in one of these NMR spectra. And so we can talk about the chemically equivalent hydrogens. So remember, I already talked about the methanol here, where we have this one peak right here for all 3 of these hydrogens. And that's because all 3 of those hydrogens are in the exact same chemical environment. And this hydrogen here is in its own chemical environment, and so it has a different peak. And so each peak corresponds to a particular chemical environment. And so if all of the hydrogens here, all 3 of these, are in the exact same chemical environment, they will all add to the single peak there. And so we can look at that with this one right here. So again, all 9 of these hydrogens are in the same chemical environment, so they all contribute to that peak, where these 3 here are in a single chemical environment, so they all contribute to that peak right there. So this is a methyl butyl ether, and it has 2 types of protons, so that will give us 2 signals. So the chemically equivalent hydrogens on the methyl group give a signal at delta 3.2, and the chemically equivalent hydrogens on the tert-butyl group give a signal at delta 1.2. And we can look at this for a somewhat more complex molecule here. So again, we have these 9 hydrogens. They are all equivalent, so they all go into this peak. These 3 right here are all equivalent, and they are all in this peak. Then these 2 hydrogens here are equivalent, and so they all contribute to that peak right there. And those are the only hydrogens found on here. We can see these 2 are going to show up the furthest left because they are next to this oxygen and this oxygen right here, where these 3, or well, these 9 are actually 3 bonds away from this oxygen. Then these 3 right here are 3 bonds away from this oxygen, and so they will not show up quite as far to the left as these ones right here, these 2 right here. So this is the tert-butyl acetoacetate, and this has 3 types of protons, which give 3 signals. So the chemically equivalent hydrogens on the tert-butyl group are at the 1.5 right here. The chemically equivalent hydrogens on the methyl group that are de-shielded by the adjacent carbonyl give this one at 2.25, and the 2 chemically equivalent hydrogens adjacent to the 2 carbonyls giving one at 3.35 over there. And so that was everything I wanted to talk about in this video. Like I said, the next one I will cover splitting. And so I hope you found this helpful, and I will see you in the next one.